The scientists believe that this idea could explain several cosmic mysteries. For example, black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Another factor that could play a role in this scenario is torsion. In extended theories of general relativity, such as Einstein-Cartan relativity, torsion is a property that accounts for the intrinsic spin of particles and can influence space-time curvature. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward, potentially giving rise to a new universe inside. Now consider the Big Bang. The Standard Model tells us that the universe began as a singularity, a point of infinite density, just like the center of a black hole. If our universe is actually the interior of a black hole that formed in a larger parent universe, it would mean that the Big Bang was not an explosion in empty space, but rather the moment matter collapsed into a black hole, creating a new universe inside. This has another implication. Each and every black hole in our universe could be the doorway to another baby universe. Every time a massive star collapses, every time matter crosses an event horizon, it might be creating an entirely new cosmos, complete with its own space, time, and physical laws. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. It's cosmic natural selection on the grandest scale imaginable. According to the study's authors, this unexpected finding, which contradicts existing cosmological models, may hint that our universe itself is inside a black hole. Now, before you dismiss this as wild speculation, let me walk you through the physics, because what we're about to discuss isn't science fiction. It's a serious theoretical framework that's been developed over decades by some of the most respected physicists in the world. And the new JWST data is giving us the first observational hints that it might actually be correct. To understand this, we need to look at the physics of black holes. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Anything that crosses this boundary is forever lost to an outside observer. However, what happens inside the event horizon is still a mystery. This is where black hole cosmology comes in, also known as Schwarzschild cosmology. It suggests that our observable universe might actually be the interior of a black hole within a larger parent universe. Think about that for a moment. Everything we see, every galaxy, every star, every planet might exist within the event horizon of a massive black hole in a larger cosmos we can never observe. But there's something even more extraordinary buried in this data, something that's forcing cosmologists to ask a question we never thought we'd seriously consider. What if our entire universe exists inside a black hole? I know how that sounds. But stay with me, because the evidence is more compelling than you might think. And it all starts with a peculiar observation about how galaxies spin. According to a new research study, the majority of galaxies appear to be rotating in the same direction. Not randomly, as we would expect in a truly isotropic universe, but with a preferred orientation. A cosmic handedness that shouldn't exist if the universe formed from a perfectly symmetric Big Bang. The lines formed by the peaks in the data allow us to identify the direction of the curve of the arms of the galaxies and consequently their spin direction. This is significant because in a truly random universe, galaxy rotation should be roughly evenly split between two directions. Using the powerful James Webb Space Telescope, scientists at the University of Missouri looked deep into the universe and found something unexpected. 300 objects that are far brighter than they should be, far brighter than any model of early galaxy formation can explain. Scientists are now calling these mysterious objects candidate galaxies, meaning they could be galaxies at the edge of time. If confirmed, that would challenge current ideas about how and when galaxies formed in the early universe. On top of that, these objects seem to have existed when the universe was only a few 100 million years old. But according to the standard model of cosmology, that shouldn't happen. During this time, the first stars and galaxies were just beginning to take shape. The universe was still in its infancy. And yet, here we are, staring at objects that appear fully formed, impossibly bright, and fundamentally at odds with everything we thought we understood. Thank you for joining me on this journey through some of the most profound questions in cosmology. The story is still unfolding. The most important discoveries may be yet to come. Keep watching the skies. Keep asking questions. Keep demanding that we follow the evidence, not our assumptions. Because somewhere in the data streaming back from JWST, somewhere in the patterns of galaxy spins and the light from the earliest cosmic dawn, lies the truth about our universe and our place within it. And whatever that truth turns out to be, it will be more wonderful and more strange than we ever imagined. And that's exactly where we should be, because that's where discovery happens. The JWST survey has given us a glimpse of something extraordinary. 300 objects that shouldn't exist according to our models. A preferred spin direction that challenges the cosmological principle. Evidence that the early universe was far more active and complex than we thought. These observations are forcing us to reconsider fundamental assumptions about cosmic structure and evolution. And one of the most intriguing possibilities is that our universe exists inside a black hole, rotating in a larger parent cosmos. It's a radical idea, but the evidence is mounting, and we owe it to ourselves, to the pursuit of truth, to follow that evidence wherever it leads. With each new observation, we'll refine our understanding, we'll test predictions, we'll rule out alternatives, and gradually we'll converge on the truth. That's how science works, not through sudden revelations, but through patient accumulation of evidence, careful analysis, and honest assessment of what the data is telling us. The black hole cosmology framework is one hypothesis among several. But it's a hypothesis that's gaining support from multiple lines of evidence. And that makes it worth taking seriously. In the coming years, we'll know more. We'll have better data, more sophisticated models, and clearer tests. And we'll be able to say with greater confidence whether this framework is correct or whether we need to look elsewhere for answers. But for now, we're in that exciting phase of science where the questions are bigger than the answers, where the data is surprising us, where we're forced to think in new ways about old problems. So where does this leave us? What should we make of the JWST observations and the black hole cosmology framework? I think we're at a pivotal moment in cosmology. For the first time, we have instruments powerful enough to probe the earliest moments of cosmic history. We're seeing things that challenge our models and force us to think more deeply about the nature of the universe. The 300 candidate galaxies found by JWST, the preferred spin direction, the chemical richness of early galaxies, these aren't just curiosities, they're clues to something fundamental. Whether that something is black hole cosmology or some other framework we haven't thought of yet, I don't know. But I do know that we can't ignore the evidence. The universe is telling us something. It's showing us that our current models are incomplete. And we have a responsibility as scientists to listen, to follow the data wherever it leads, even if it takes us to uncomfortable places. The answer is yes, it is testable, but indirectly. We can't directly observe the parent universe or the event horizon we're inside, but we can look for signatures that would be expected if this framework is correct. The preferred galaxy spin direction is one such signature. The axis of evil in the CMB is another. The rapid formation of massive galaxies in the early universe could be another. If we continue to find evidence that the universe has a preferred direction, that it's rotating, that would strongly support the black hole cosmology framework, we can also look for other predictions. For instance, if the universe underwent a big bounce, rather than starting from a true singularity, there might be signatures of that bounce in the CMB or in the distribution of matter on the largest scales. These are subtle effects, but with instruments like JWST and future telescopes, we might be able to detect them. The key is to make specific, quantitative predictions that can be tested against observations, and that's exactly what researchers are doing now. The idea that we might be inside a black hole is certainly uncomfortable. It challenges our sense of cosmic significance. It suggests that our universe, vast as it is, might be just one of countless others, nested inside black holes in an infinite fractal structure. But discomfort isn't a reason to reject an idea. If the evidence supports it, we need to take it seriously. And right now, the evidence is intriguing. Not conclusive, but intriguing enough that we need to pursue it further. The JWST is just beginning its mission. Over the coming years, it will observe thousands more galaxies, probe deeper into cosmic history, and provide us with unprecedented data about the early universe. The Nancy Grace Roman Space Telescope will launch later this decade, adding its capabilities to the mix. And there are proposals for even more powerful telescopes that could push our observations back to the very first moments after the Big Bang. From our perspective, the universe appears to be expanding in all directions because we're in an expanding region of space-time created by the bounce. Second, if every black hole is a universe, why don't we see evidence of this when we study black holes in our universe? The answer is that we can't. By definition, we can't observe what's inside an event horizon. Once matter crosses the horizon, it's causally disconnected from us. We can't send signals in, and no signals can come out. If there are baby universes inside the black holes in our universe, they're completely isolated from us. They have their own space and time, and from their perspective, they're the entire universe. Third, doesn't this just push the problem back? If our universe is inside a black hole in a parent universe, where did that parent universe come from? And that's how science works. You don't prove a theory with a single observation. You build a case by accumulating evidence from multiple sources, each piece reinforcing the others. We're at the early stages of building that case for black hole cosmology, but the foundation is solid, and the JWST data is adding crucial new support. Let me address some of the objections that have been raised to this framework, because there are legitimate questions that need to be answered. First, if we're inside a black hole, why don't we see an event horizon? Why does the universe appear infinite in all directions? The answer is that from inside a black hole, you can't see the event horizon. It's not a physical surface, it's a boundary in space-time. Once you're inside, all paths lead toward the singularity, or in the case of a rotating black hole with torsion, toward the bounce point. But because space-time is expanding, because of the big bounce, we're moving away from the center, not toward it. The expansion of the universe is the rebound from the bounce. Yes, it does push the question back, but it also provides a framework where universes can exist eternally, creating each other in an endless cycle. There's no need for a first cause or a beginning of time. The multiverse has always existed and always will. Some might find this unsatisfying, but it's no more unsatisfying than the alternative, which is that our universe sprang into existence from nothing for no reason. At least the black hole cosmology framework provides a mechanism, a physical process by which universes can be created. Fourth, is this testable? Can we ever prove or disprove this theory? This is the most important question. A theory that can't be tested isn't science, it's philosophy. For decades, cosmologists have studied these fluctuations, looking for patterns that might reveal the physics of the Big Bang. And they've found something intriguing. There's a hint of a preferred direction in the CMB, a slight asymmetry that shouldn't exist if the universe is perfectly isotropic. It's called the axis of evil, a somewhat tongue-in-cheek name for a very serious anomaly. The axis of evil is a statistical alignment of the largest scale temperature fluctuations in the CMB. They seem to be oriented along a particular direction in space, rather than being randomly distributed. This has been controversial. Some scientists argue it's just a statistical fluke, an artifact of how we analyze the data. Others think it's real and points to something fundamental about the universe's structure. If the universe is inside a rotating black hole, the axis of evil might be the signature of that rotation. The preferred direction in the CMB could be aligned with the rotation axis of the parent black hole. Combined with the preferred galaxy spin direction found in the JWST data, we're starting to see a consistent picture, multiple independent observations all pointing toward the same conclusion. The universe has a preferred direction. It's rotating, and if it's rotating, the most natural explanation is that it's inside a rotating black hole. Now, I want to be clear about the level of certainty here. This is still a hypothesis. We don't have definitive proof, but we have multiple lines of evidence that are all consistent with this framework. The JWST observations of unexpectedly bright early galaxies, the preferred spin direction of galaxies, the axis of evil in the CMB, the fine-tuning of physical constants, the need to explain what came before the Big Bang. Each of these individually might have alternative explanations, but together they form a pattern that's hard to ignore. But in black hole cosmology, the Big Bang isn't a true singularity. It's the moment of rebound after a collapse in a parent universe. The Big Bounce, this is where Einstein-Cartan theory comes in. In standard general relativity, matter collapses to an infinitely dense point at the center of a black hole. But Einstein-Cartan theory includes torsion, a property related to the intrinsic spin of particles. Torsion creates a repulsive force at extremely high densities. As matter collapses and density increases, eventually, the torsion-induced repulsion becomes strong enough to halt the collapse and reverse it. The result is a bounce. The collapsing matter rebounds, creating an expanding region of space-time. From the inside, this looks exactly like a Big Bang, an explosive expansion from a hot, dense state. But from the outside, in the parent universe, it's just a black hole. Matter fell in, crossed the event horizon, and disappeared from view. What happens inside is invisible to external observers. This framework elegantly connects black holes, the Big Bang, and the possibility of a multiverse. Every black hole is a universe. Every universe contains black holes that are themselves universes. It's a fractal, self-similar structure extending infinitely in both directions. And the JWST observations of early galaxies and preferred spin directions might be giving us the first observational evidence that this framework is correct. But there's another piece of evidence that supports this idea, and it comes from the cosmic microwave background, the CMB. The CMB is the afterglow of the Big Bang, radiation that's been traveling through space for over 13 billion years. It's remarkably uniform, with temperature variations of only about 1 part in 100,000. But it's not perfectly uniform. There are tiny fluctuations, and those fluctuations tell us about the conditions in the early universe. The black hole cosmology framework offers an elegant solution. If universes are created inside black holes, and if the properties of those universes depend on the properties of the parent black hole, then we have a mechanism for cosmic natural selection. Universes that have constants conducive to forming stars and black holes will produce more black holes, which in turn create more baby universes with similar properties. Over countless generations, the population of universes would be dominated by those with life-friendly constants. It's not that our universe was designed for life, it's that universes like ours are more likely to exist because they're better at reproducing. This framework also addresses another deep mystery, the origin of the Big Bang itself. In the standard model, the Big Bang is a singularity, a point where our physics breaks down and we can't say anything meaningful about what came before. We've built our entire cosmological framework on this assumption. The Big Bang model, dark energy, cosmic inflation, all of these rely on the universe being fundamentally symmetric. But if galaxies have a preferred spin direction, that symmetry is broken, and we need to understand why. One possibility is that the universe may have a preferred axis. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. Let me walk you through the theoretical framework that could explain this. In any case, the universe is turning out to be far stranger than we ever imagined, and the uneven galactic rotations will likely prompt astrophysicists to reassess certain aspects of our understanding of the universe. But let's dig deeper into the black hole cosmology framework, because there's more to this theory than just explaining galaxy spins. One of the most profound mysteries in modern physics is why the universe appears fine-tuned for life. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, all seem to be precisely calibrated to allow for the existence of stars, planets, and ultimately, life. Change any of these constants by even a small amount, and the universe would be radically different. Stars might not form, atoms might not be stable, chemistry as we know it might not exist. This fine-tuning problem has puzzled physicists for decades. Why are the constants what they are? Is it just luck? Is there some deeper principle we're missing? So what could they be? The ultimate confirmation will come from spectroscopy, the most reliable method available. By separating light into its component wavelengths, much like a prism creating a rainbow, scientists can analyze a galaxy's distinctive signature. This will reveal crucial details about the objects that we are seeing, their distance, their composition, their velocity, and whether they're truly ancient galaxies or something else entirely. The implications are enormous. If these really are fully formed galaxies existing just a few 100 million years after the Big Bang, then our theories about how matter comes together in the universe may need to be rewritten. If they're not, then we might be looking at a new phenomenon, one that played a key role in shaping the universe's earliest days. Up until 2022, the most distant galaxy we'd ever seen was GNZ 11, spotted by the Hubble Space Telescope. It was a landmark discovery. Hubble, with its 2.4-meter mirror and incredible optics, had taken us deep into space, but there was a limit to how far it could see. If our universe is the interior of a black hole in a larger parent universe, then it inherited certain properties from the collapse that created it. One of those properties could be angular momentum or spin. When a massive star collapses to form a black hole, it typically has some rotation. That rotation doesn't disappear, it gets encoded into the structure of the black hole itself, creating what we call a Kerr black hole, a rotating black hole. Inside a rotating black hole, space-time itself is dragged around by the rotation. This effect, called frame dragging, means that anything inside the black hole, including space itself, is forced to rotate in the same direction as the black hole's spin. If our universe is inside such a rotating black hole, then the frame dragging effect could explain why galaxies have a preferred spin direction. They're not spinning randomly, they're being influenced by the rotation of the space-time they're embedded in. This is testable. If the preferred spin direction is real and not a statistical fluke, then we should see it consistently across different surveys and different regions of the sky. We should also see correlations between galaxy spin and other large-scale structures. The JWST data is giving us the first hints that this might be the case, but we need more observations to be certain. Moreover, the existence of ancient, massive galaxies so soon after the Big Bang challenges our understanding of cosmic evolution. But while the universe inside a black hole theory is tantalizing, there could also be a more pedestrian explanation for the unexpected observations. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. If our local measurements are off, that could skew our understanding of how galaxies form and evolve on cosmic scales. But MOMS-Z14 is telling us that multiple generations of stars had already lived and died before it formed. That means galaxy evolution may have started much earlier than we thought. It raises a big question. How many more galaxies like MOMS-Z14 are out there? Before JWST, we thought galaxies this early would be incredibly rare, but now we've found more than we ever expected. These ancient bright galaxies, sometimes called little red dots, are popping up across JWST's surveys, and astronomers now believe that MOMS-Z14 may be the record holder as of now, but it might not be for long. The more we look, the more we find, and every discovery chips away at our assumptions. If galaxies like MOMS-Z14 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? Does this challenge our cosmological models? In a word, yes. Our current understanding of galaxy formation says that these kinds of galaxies should be rare, slow-growing, and simple. MOMS-14 is none of those things. It's fast, bright, and chemically complex. It's not that our models are wrong, but they're incomplete. MOMS-Z14 is a clue that the early universe might have been far more active than we imagined. And this is just the beginning. Later this decade, the Nancy Grace Roman Space Telescope will join JWST in scanning the early universe. Roman will cover much larger areas of sky with incredible detail. Together, these telescopes could uncover hundreds, maybe thousands of galaxies like MOMS-Z14, each one a time capsule from an era we're only beginning to understand. But for now, MOMS-Z14 stands as a milestone, a flicker of light from when the universe was still finding its footing. But the more we probe JWST's findings, the more the universe defies expectations. And that brings us back to the most extraordinary claim, that the majority of galaxies appear to be rotating in the same direction. There's no sign of a supermassive black hole. Most of the galaxies we've studied with intense star formation host a supermassive black hole at their center. These black holes are thought to play a key role in galaxy evolution, regulating star birth, shaping structure and driving growth. But MOMSZ14 doesn't have one, at least not one we can detect. The mysteries don't stop there. When astronomers used JWST's spectrograph to analyze the galaxy's light, they found it rich in nitrogen, unusually rich. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that MOMSZ14 is forming stars in extremely dense environments. That's not what we expected. Galaxies this early in the universe should be chemically simple, mostly hydrogen and helium. The first stars, what we call population 3 stars, should have been made almost entirely of primordial elements because heavier elements like carbon, nitrogen, and oxygen are only created inside stars and dispersed when those stars die. Then the James Webb Space Telescope was launched. Armed with a massive 6.5-meter mirror and tuned to infrared, the exact kind of stretched ancient light that early galaxies emit, Webb didn't just continue Hubble's work, it crushed its records. In one of JWST's early campaigns, a galaxy named JWST 14-0 was found. It held the record for the most distant confirmed galaxy with a redshift of 14.32. Redshift, in a nutshell, is how much the light from a galaxy has been stretched by the expansion of the universe. The higher the redshift, the older the light. Then came MOMSZ14. With a redshift of 14.44, it pushed our view even deeper into time. And it wasn't just the redshift that stunned scientists, it was what the galaxy actually looked like. This galaxy is tiny, about 500 light-years wide. For comparison, our Milky Way spans over 100,000 light-years, but MOMSZ14 is also incredibly bright. Normally, galaxies this early in the universe should be faint and hard to detect. Not this one. MOMSZ14 is bursting with newborn stars, a rapid-fire stellar nursery in the first few chapters of cosmic history. But one feature, or rather the absence of one, made it even stranger. Let me explain why this is so significant and what it might mean for our understanding of cosmic structure. In a perfectly isotropic universe, one that looks the same in all directions, galaxy spins should be random. If you surveyed a large enough sample, you'd expect roughly 50% spinning clockwise and 50% spinning counterclockwise from any given vantage point. But that's not what the data shows. When researchers analyze the morphology of distant galaxies, looking at the spiral arm patterns and rotational indicators, they found a statistically significant bias. More galaxies spinning in one direction than the other. The probability of this occurring by random chance in a truly isotropic universe is about 0.2%. 1 in 500. That's not impossible, but it's unlikely enough that we need to take it seriously. This finding, if confirmed by additional surveys, would violate one of the fundamental assumptions of modern cosmology, the cosmological principle. This principle states that on large scales, the universe is homogeneous and isotropic, the same everywhere and in every direction. The scientists continued by adding that rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing, self-replicating process. And now, the JWST data is giving us the first potential observational evidence that this framework might be correct. Let me show you exactly what we've found and why it's so profoundly important. To identify each of the 300 early galaxy candidates, the scientists used a method called the dropout technique, which detects high redshift galaxies by looking for objects that appear in redder wavelengths but vanish in bluer ones. This technique works because as light travels across the expanding universe, it gets stretched. The farther away an object is, the more its light is redshifted toward longer, redder wavelengths. At extreme distances, the ultraviolet and visible light emitted by early galaxies gets shifted all the way into the infrared spectrum. That's why JWST, with its powerful infrared capabilities, is so revolutionary. It can see light that's been traveling for over 13 billion years, light from galaxies that formed when the universe was less than 5% of its current age. After spotting these objects, the next step is to check whether they could be at very high redshifts. Could they be even farther away than we expect them to be? Because in the past, scientists often thought these extremely bright objects weren't early galaxies, but something else that mimicked them. Quasars, for instance, or foreground objects that happen to have similar colors. The lead scientists of the discovery believe that even if only a few of these objects are confirmed to be in the early universe, they will force us to modify the existing theories of galaxy formation.